Okay, good morning. What we're going to do today is go through the exam paper you did before half term. Obviously, if you're happy with the questions, you can skip through to the parts of the video that you think you were struggling with. But I'd like to briefly go through all of the questions. And if you finish in time, perhaps you could write a reflection on your exam. Let me know what you thought of it. So without any further ado, we'll start with question 1. Please make sure you've got your exam paper in front of you so you can see it, so you can check your individual answers. In what form is energy stored in a battery? So an energy transfer diagram for a battery would of course be chemical to electrical, and then to whatever you want after that. It could be light, it could be kinetic if it's a motor, etc, etc. So the energy is going to be chemical energy. This one, the answer is going to be D. Nice and easy to start with. Question 2. What main store of energy is the electrical energy converted into when powering a kettle that boils water? So again, another energy transfer here. We've gone from electrical, which is what the chemical is using. In this case, it's dead easy. It goes straight to thermal. Kettle gets hot. So the answer should be thermal, which is B. Question 3. A frisbee is thrown with a velocity of 2.6 meters per second. If the mass is 150 grams, how much kinetic energy does it have? So let's write down the information we've got. We've got a velocity of 2.6 meters per second, and we've got a mass of 150 grams. Now straight away, we need to make sure these are in standard units before we apply any equations, and they are not. The mass is in grams, and in fact it should be kilograms. So I'm going to rewrite the mass. I'm going to divide by 1,000 to convert it into kilograms, 0.15 kilograms. And you must use that in any equations. Next, we need to just apply the kinetic energy equation. It's a required equation. It's one that you need to learn. There's no getting away from it. It won't go away. So make sure you memorise that one. And then plug in the numbers. Putting in 0.15, putting in 0.15 here, not 150, and then we're only squaring the 2.6, so it's 2.6 squared, which should give us our answer of about 0.5 joules. So the answer is A. Okay, question 4. A cliff diver has 2,380 joules of kinetic energy just before they enter the water. If that diver has a mass of 63 kilograms, how fast is the diver travelling before hitting the water? So this is using the kinetic energy equation again, but this time we want to manipulate this equation to get V, because after the velocity we have the mass and it's in standard units. That's fine. Energy is in standard units. We want V, this guy here. So I'm going to multiply through by 2 to give me 2ke equals mv squared, and then going to divide by m, and that will cancel out the m there, and then I'm going to take the square root of both sides. That will get rid of the v squared, which leaves me v is square root 2ke over m. And we've got all the information now, so that's square root of 2 times the kinetic energy, which was 2380, divided by the mass. It's already in standard units, which is 63. So that gives us an answer of about 8.7 or 8.69 meters per second. So your answer for this one is B. Right, okay, let's get rid of all this. Moving on to question 5. Right, on to question 5. So a drill contains an 85 watt motor and is used for continuously for 1.3 minutes. How much energy does the motor in the drill use? So to answer this one, let's look at our definition of power first of all. Power is the rate at which energy is transferred, or energy divided by time. Now we of course want to work out the energy here, so we need to manipulate this equation, and that simply goes to energy is power times time, and then it's just a case of plugging the numbers in. But the time has to be in seconds. Now we're told it's 1.3 minutes, and we need to convert that into seconds. There's many ways you can do this. It's quite easy. 0.3 minutes will equal 18 seconds. You can do this in your head or work it out. Well, basically 0.1 minute would be 6 seconds, times that by 3 gets you 18. So that gives us 78 seconds in total, because it's 1.3 minutes, so 60 plus 18 gives us 78, and then multiply that by our power, so 85 times 78, and that gives us 6,600 joules. So the answer is A. Question 6. Which of the following statements is not true? I won't write these down, I'll just read them out to you. The total energy in a closed system is constant. That is true. Energy conservation. Energy cannot be created or destroyed. We all know that to be true. It's the fundamental principle of physics. The total energy in an open system is always constant. No, that's not true. An open system means that energy can come from other sources. So it's definitely C, which is the incorrect one, and D, energy can be transferred from one source to another. In a closed system, yes it can. So answer is C. What's happening here is that there's some external force or some external energy being fed into the system, which makes it look like it's violating energy conservations, but it's not, because that energy had to come from somewhere else. Question 7. Which of the following actions will increase the efficiency in a house? Reducing the thickness of the walls? Well, no, making the walls thinner will mean that energy can escape easier. Increasing the number of windows and external doors into the house? No, windows and doors are good ways to lose heat. They're not very thermally insulating. They conduct quite well, so they're bad. Moving the heaters and radiators into the attic, well, that's not going to work, because if you imagine your house, sorry about my drawing here, but heat is always going to rise. So if I put my heater at the top, then down here will be cold. Your attic will get very hot, but the rest of the house will be extremely cold. Increasing the amount of insulation in the walls, yes, that will definitely increase the efficiency, because it will warm up quicker and it will stay warmer for longer, so you won't have to have your heaters on for quite as much. So the answer is D. Right, question 8. So a research engineer is investigating the thermal conductivity of 4 new materials her company has created. Rods of each materials are heated at one end. After 5 minutes, the temperature of each rod is recorded at 5 points along the rod. The data is displayed in the table below. So we've got some kind of rods here. The question doesn't say this, but I'm assuming that we started at room temperature and we're applying heat at one end here. Now if this is conductive, the heat will transfer more quickly. So after 5 minutes, this end over here will be hotter. Won't reach the same temperature, but it will be hotter if it's a good conducting material. If it's an insulating material, it will remain at room temperature. So all we've got to do really is look at the start point and the end point of the data and see which ones has the smallest temperature change. It's not just the final temperature, it's the smallest temperature change, and the one with the smallest temperature change is B. That goes from 75 and it only reaches down to 62, so that's a change of 13 degrees C. which is much smaller than the rest of them. So it's obviously heating up quicker because the energy can get there faster, i.e. it's more conductive. Right, on to question 9. I'll get rid of that. So question 9, which of the following energy resources is not renewable? Renewable source can be used over and over again. You either know this or you don't. Wind is, coal isn't, tidal is, and hydroelectric is. So the answer is B. I don't think anybody got that wrong. That was quite easy. Question 10. What is the potential difference across a 380 ohm resistor if the current flowing through it is 8.9 milliamps? So we have 380 ohms and 8.9 milliamps. Like before, what we need to do is instantly convert this one, because that's in milliamps, we want it in amps, so that will be the same as saying 0.0089 amps. And we must use standard units, otherwise the formulas won't work. For this, we're going to use Ohm's law. So voltage is proportional to current, or V equals IR. Potential difference is voltage. It's the same thing. So voltage equals the current, which I'm putting in standard units, 0.0089 multiplied by 380. And that should give us about 3.4, I think. Yeah, so 3.4 volts. That is answer B, I believe. Yeah. Right, question 11. A 650 milliamp current flows through a single loop circuit. The only components in the circuit are the battery and a 55 ohm resistor. If the resistor is changed for another resistor with double the resistance, what is the new current in the circuit? So we've got a very simple circuit with one resistor in. We've got 650 milliamps or 0.65 amps. I'll convert that straight away this time. And a 55 ohm resistor. There's two ways you could do this. I could work out the voltage. So I could work out voltage equals 0.65 times 55, and then plug in a new value for the resistor and changing it. But actually there's a simpler way. If we look at this relationship up here, I can say that if I'm going to keep V a constant, if I'm going to double the resistance, so we've got V equals IR, this one is going to be a constant, that's not changing, the question says that. Then if I were to double this value, then I would have to half that value in order to get the same answer over here. So really all I need to do is half the current, so that would give me about 0.33 amps, which is answer A. And finally, I'll just do it up here, I'm running out of space. Question 12. Two 370 ohm resistors and an 85 ohm resistor are connected in series. What is the total resistance of these three resistors? We just add them together, but please do read the question. There are two 370 ohm resistors, not one. I think that caught a few people out. And an 85 ohm. In series, resistances just add together. So just adding them all up, and the I'm trying to do this in my head. The answer is 825 ohms, which gives us answer B. Okay, on to question 13. So students investigating the IV characteristics of an unknown component, not including a power supply or battery, what three circuit components must the student connect to this unknown component to be able to record its IV graph? So a standard circuit, which we definitely need to know. It looks pretty much like this. The components can go in any order because it's a series circuit. And this thing here, it's a resistor, but we'll call it X. That's the unknown component. And remember, we need a voltmeter in parallel just over it. So the three components we need are, of course, the ammeter, the voltmeter, and a variable resistor. That's to adjust the current so we can get a range of results so that we can plot a graph. We need that to change things, otherwise you'd only be able to take a single reading. So the answer is D. Question 14. What is the voltage across the 250 ohm resistor in the circuit to the right? So we've got two components. This time they're wired in parallel, so this is very easy. We've got 4.5 volts at the top, and the rules are for parallel circuits the voltage is always the same, so it doesn't matter what the resistance is, the voltage will be 4.5, which is answer B. And on to question 15. So a solar panel has an efficiency of 32.5%. During the average day, it receives 1.71 times 10 to the power 6 joules of energy. And considering the solar panel to only generate power for 9.5 hours, alarm bells should be ringing here because hours is not a standard unit. What is the average power output from the solar panel during these 9.5 hours? So the first thing I want to do is convert this 9.5 into standard units. There are 3600 seconds in an hour, so 9.5 times 3600, and that gives you 34,200 seconds. Next thing we need to consider is the power equation. Power is the rate of energy transferred, so energy over time taken. And now we can just plug these numbers in. The energy, 1.71 times 10 to the 6, it's in joules, so that's fine, divided by the time in seconds, 34,200, and that gives you 50. But of course that is not the right answer because it's only 32% efficient. So I need to multiply that by 0.32 in order to get the actual power output of 16 watts. So the answer is D. On to question 16. A spring is extended by 2.4 centimetres. And before I go any further, I'm just going to rewrite that in standard units. That's 0.024 metres, resulting in 0.043 joules of elastic potential energy. What is the spring constant? So energy stored in a spring, it's a tough equation. It's 1/2 kx squared, where x is the extension, k is the spring constant, and E is the energy stored. So we need to manipulate this for k, because it's this one that we're after. So k is going to be equal to 2E divided by x squared. Plug my numbers in. 2 times 0.043 divided by 0.024. Remember, this is in meters squared, and that gives you an answer of 150 newtons per meter. So that would be answer D. On to question 17. What is meant by a non-contact force? A non-contact force is simply a force that acts between two objects that aren't touching. That will be answer B. Question 18. We've got an airliner which has a mass of 41,000 kilograms. That is the standard unit, that's fine. With 18,000 kilograms of fuel and 20,000 kilograms of passengers and luggage and stuff. That might seem an unusual number, but that only equates to about 160 passengers, so that's perfectly fine. We want to work out the weight. Remember, weight is a force, it's not its mass, and it's given by W equals mg. So W equals, we need to add all the masses together first. So 41,000 plus 18,000 plus 20,000 to give you your M, and then multiply that all by G. They're giving you G here, so we'll take it as 9.8 newtons per kilogram, and that will give you an answer of 770,000 newtons, which we can rewrite as 770 kilonewtons. So that will be answer D. Question 19. Where are we? So we've got an object with two forces acting on it. One to the right, one to the left. 23.5 and 16.8, and we want to work out the magnitude of the force. Now normally here you quote a direction as well, but the question does ask for the magnitude, so it doesn't really matter which way it's going. It's not asking for that, it's just asking for what the value of that number is. So I'll just take the biggest one and take away the smallest one. 23.5 minus 16.8, 6.7. Now that would be 6.7 to the right, but we're not interested in that, we're just after the number. So 6.70, answer is B. And question 20. Spring is extended by 17 centimetres when a 45 Newton force acts upon it. What is the spring constant? So it's different to the energy in a spring. When we've got a force involved, it's simply K X, where K is the spring constant and X is the extension. We want K, so manipulating this and dividing by X on both sides to cancel that out. So K is F over X. The force is fine, that's 45, but the 17 centimetres needs to be converted into metres, so we'll write that as 0.17. And that gives us 260 newtons per metre. Now be careful with this because there's two 260s in the multiple choice. It is A because it's a units, newtons per metre, which we're after, which looks right because that's measured in newtons, that's measured in metres, so it would be newtons per metre. Right, question 21. A train travels 658 metres in 3.75 minutes. That's not a standard unit, so watch out for that. What is average speed? Speed is simply the rate at which something moves, so distance over time. So we'll do 658 divided by, now the time has to be in seconds for this, in standard units, so that would be 3.75 times 60, and that gives us 2.92 metres per second, which must be quite a slow train, but hey ho. Question 22. A car accelerates on the motorway from 12 metres per second to 16.5 in 25 seconds. What is the acceleration of the car? So this is using one of the SUVATs. Acceleration can be given by the change in velocity divided by the time taken, because that's the definition of acceleration, how fast something's velocity is changing. We've got all the numbers we need for this, and they're all in standard units. Oops, computer's going weird. And they're all in standard units, so there's no problem. It's simply 16.5, the final velocity, minus 12, divided by 25, or 4 over 25, which gives us 0.18 metres per second squared. Question 23. What is the velocity described by the distance time graph? I'll just sketch it out, although you should have it in front of you. On a distance time graph, the gradient gradient gives you the velocity, because it's the rate at which the distance is moved through. So all we need to do is work out the gradient. With a straight line like this, we should try and use as much of the graph as possible. Don't do a tiny little gradient like that. I know it looks nice and neat, but it's really not very good. So I'm going to do a big gradient, and I can see that the change is from 3.5 to 0.5. So that's a change in distance of 3 meters, and that took 2 seconds. So to work out the velocity, it's simply 3 over 2, which gives us 1.5 meters per second. Okay, question. Actually, no, I won't move that. Okay, question 24. A car travels along the motorway at a constant speed of 19 meters per second. His engine is running and providing power to the wheels. What does Newton's first law tell us about the forces acting on the car? Well, if it's Newton's first law, then the forces must be balanced because it's not changing its velocity. So the answer will be C. The force exerted by the engine is equal to the resistive forces. If the forces are balanced, it's going to obey Newton's first law, and it's going to either remain at rest or carry on in a straight line. Question 25. Which of the following is the correct calculation for stopping distance? The stopping distance is equal to the thinking distance plus the braking distance. Okay, nothing to do with reaction times or anything like that, it's those ones, so that will be C as well. Question 26. The thinking distance of a vehicle is affected by the reaction time of the driver. Which of the following is not a factor that can affect the reaction time of a driver? This always causes a little bit of confusion, because the answer is actually B. But people are going to say, why? Because if he's going faster, then surely you'll travel further. And that's absolutely correct, but the reaction time will remain the same. The thinking distance would be increased, but the reaction time remains the same. Whereas tiredness, poor visibility, intoxication, etc., they're all factors that will affect the reaction time. Question 27. A wave travels at 25 meters per second and has a frequency of 38 hertz. They're all in standard units, so this should be nice and easy. What is the wavelength? We're going to use the wave equation, V equals F times lambda. So we want the wavelength. Manipulate this, it's simply V divided by F, so that's 25 over 38, which gives you about 0.66 meters. So that is answer C. On to question 28. Which of the following correctly shows the reflection of a light ray shown to the right? So the rules for reflection, which we should know from year 9, is that any light ray coming in at an angle here, the angle of reflection, the angle of incidence, the angle of reflection will equal it, i.e. I equals R. So looking at those ones, the one there that are equal is B. Question 29. Which of the following types of EM radiation has the longest wavelength? Make sure you learn the order of the EM spectrums. So starting with the longest ones, we would have radio, then we have microwaves, then we have infrared, visible, UV, X-ray, and finally gamma. So out of those four, I think the answer is obviously microwave. There's no radios in there, so that will give us B. Question 30. Which of the following is caused by long exposure to UV radiation? Let's go through some of these answers. Increased risk of mutations in bone cells. No, that's higher energy radiation such as X-ray and gamma rays. Decreased risk of skin cancer. Absolutely not. Increased risk of atoms in cells becoming radioactive. That just doesn't happen with radiation exposure like this. It can happen with certain types of radiation, neutron radiation, but no. Premature aging of skin, yes. So stay out of the sun unless you want to look old. And question 31. Which of the following is the correct reason why greenhouse gases are causing an increase in the average temperature of the Earth's atmosphere? The answer is A, and I'll explain why. If you imagine the Earth being like this, we get sunlight coming in, which is absorbed by the Earth. Some of it's reflected around the polar caps and white clouds, but a lot of it gets absorbed. And then the Earth re-emits this energy, usually at night time or whenever it's cooler, but it comes out as infrared radiation. And greenhouse gases kind of provide this barrier here, and the infrared radiation gets trapped in these greenhouse gas in the atmosphere. So the sun's providing the energy going in, but it can't get out, which means that the planet starts to warm up. On to question 32. How does a star form? So again, this is factual based knowledge. The answer is A. Dust and gas in a nebula come together because of gravity, creating immense heat and pressure until fusion starts. And it becomes, well, it's kind of a protostar at that point. Question 33. Which of the following orbits planets? I'd be surprised if you get this one wrong. It's obviously moons. You might not know what a red giant is, but that's a star, and obviously stars are far too big to orbit planets. It's all to do with the mass of them. Question 34. What does the redshift of distant galaxies tell us about the history of the universe? So the redshift is this apparent effect where wavelengths from distant galaxies, which look like that, have been stretched out, so exaggerated. They have a longer wavelength. We have a short wavelength there, and then we have a long wavelength over here. And we know that they should be a short wavelength, but they're coming out longer. And the only explanation from that is that these things must be moving away, and that's something called the Doppler effect. So that means that the galaxies are receding away from each other, and they begin at one hot, dense point. So answer B looks to be the best fit. Question 35. What is observed in the light from most distant galaxies? So looking at this diagram up here, the observation is that the frequency is lower and the wavelength is stretched out. The speed of light doesn't change, and the range of observed frequencies, that's nothing to do with anything. So the answer has to be B. Question 36. What stellar object does the core of a red giant become after the red giant runs out of hydrogen to fuse? The answer is going to be A. Now, I know some of you might think, well, why can't it be B or C? It's obviously not D because that's how it begins. But its key is the wording. It's a red giant, not a red supergiant. A red supergiant or a red hypergiant, they go supernova and turn into a neutron star or a black hole, but it just says red giant, so the answer has to be A. It cools down into a white dwarf, which will shine for about 90 billion years, and then eventually cool down to a cold lump of metal. Right, question 37. A planet has a stable orbit around its star. The distance between the planet and the star changes as the planet orbits around the star. Which of the following is true about the planet's orbit? So, if the distance is changing, if this is the star, then the orbit must follow something like this. It's an elliptical orbit, which in fact most orbits are. And it goes slow around here because it's further away, so there's less gravity, and it goes fast at these points, and it's always accelerating towards the star at any point. So the answer will be D. The planet speeds up as it moves closer to the star. Question 38. What does the intensity of emitted radiation from a body depend on? It's to do with its temperature. The hotter things are, then the colour seems to change. It starts off with low energy, low temperatures, which are at the red end of the spectrum, and then it moves up right towards the sort of the green and the blue end, which are the shorter wavelengths, the higher frequencies. So the answer is C, temperature. 39. What is the best type of electromagnetic radiation for wireless communications and why? Visible light, not really. It doesn't refract very well, so we have to have a direct line of sight. Gamma rays, they would be too dangerous and they're absorbed easily. Ultraviolet light, it passes through the atmosphere. Yes, but again, that's dangerous, so obviously radio waves is our answer. They're the long wavelength, which reflects well, so they can go around buildings, around hills, bounce off the upper atmosphere, etc., etc. Question 40, a refraction question, which is the best diagram. So we've got two mediums, N1 and N2, the normal. Doesn't actually say, but we're going to, oh, it does say, sorry, yes, N1 is smaller than N2, so this is more dense on this side, N2 is more dense. So the ray of light is going to come flying in at an angle and it's going to bend towards the normal. I don't like using the word bend, it's going to change direction abruptly, and the best picture which describes that is B. Right, question 41, AC stands for alternating current, so your answer is A. Question 42, which of the following statements about EM waves is false? We've got four options. They don't have a wavelength is obviously false. The rest of the answers, they are transverse waves, they're not longitudinal, they all travel at the same speed and they do form a continuous spectrum, so there's no doubt about that one. Question 43. This was quite a tough one. You have to do quite a bit for 1 mark. We've got a wave here and we've got a displacement against time, and we want to work out the wave speed. So using the wave equation, v equals f times lambda, and I think we're told that lambda equals 4.1 centimeters. However, we don't have f over here. So let's try and work this out from the graph. The first thing, the displacement, that's independent of frequency and wavelength. It makes no difference. So the time taken for one complete oscillation, I reckon it's about 12.5 seconds. Now, time period and frequency can be linked by this equation. Frequency is 1 over time, and time is 1 over frequency. So that means that the frequency here must be 1 over 12.5. 1 over 12.5, and then plugging that into the wave equation, 1 divided by 12.5, which is our frequency. I'll leave it as it is, multiplied by, now I'm going to keep this, it's a bit naughty, I'm going to keep this in centimetres for now, multiplied by 4.1 centimetres, but I know that my answer will come out in centimetres per second if I do that. And that gives about 0.33 centimetres per second, which is not one of the options. But option B is 3.3 millimetres per second, which is actually the same as that. So the answer must be B. On to question 44. We've got this kind of 3D diagram, which is odd to kind of comprehend. We've got to identify what type of wave it is. Clearly it should be a transverse wave because the oscillation of the particles is perpendicular to the direction of propagation. So your answer will be B. Question 45. Stopping distance of a lorry is measured by a safety regulations company. and they test the stopping distance when it's travelling at 5, 10, 15 and 20 metres per second. Which of the following measured stopping distances correctly corresponds to the stated speeds? Now, of course, I don't expect you to know stopping distances for lorries. You're year 10, you haven't started to drive yet. But what we do expect to know is really this equation, which is KE equals half mv squared. Now, what that tells me is that the energy in the lorry is not only going to increase with its speed, but the rate at which it's going to increase is going to increase as well. I.e., if I'm going twice as fast, because of the v squared term down here, I'm going to carry 4 times as much energy. So what I'm looking for is 4 numbers that are increasing, but the rate at which that increasement is increasing as well. They're not going in even increments. Now, A is obviously wrong because there's an anomaly at 15 metres, so it can't be that. C, the distance is getting smaller as it's getting faster, which makes no sense whatsoever. B, that looks like to be the correct one. We got 20, 45, 75 and 120. So you can see that the difference between here and here, that's only 25, and the distance from there to there is 30, and the distance from there to there is 45. So it's obviously getting bigger. D is also getting bigger, but the increments are getting smaller, which wouldn't happen. So your answer is going to be B. Question 46. Try and squeeze this on down here. We've got a graph. This is a velocity time graph. So the thing that we need to know from these types of graphs is that the gradient equals your acceleration, and the area under the graph will equal your displacement. So we want to calculate the acceleration. Like the previous question, I'm going to use as big a triangle as possible. So we're looking at the difference from here. Now, I reckon that's 6 and 3.5, so that's a difference of 2.5 divided by the time taken, which is 15. And remember our definition of acceleration, rate of change of velocity, well, that's kind of what you just worked out. So if I do 2.5 divided by 15, that gives me about 0.16 metres per second or so, and that's rounded up to 0.17, whoops, don't forget your units, metres per second squared. It's an acceleration. The answer, 0.17 metres per second squared, D, is the answer that fits. Elephant is dropped out of the back of the plane. It's got a parachute. I don't know who writes this. Before the parachute opens, we've got a graph which looks a velocity time graph, which kind of roughly looks like that. So velocity against time. What is the cause of the constant velocity after 20 seconds of free fall? So the constant velocity is this bit where it starts to level off. And the reason that is not because gravity gets weaker or anything like that, but our elephant, which I won't draw, I'll try. There's his trunk and 4 legs. The gravity mg is going to be balanced by the air resistance pushing it back up. So it's going to obey Newton's first law and travel at a constant velocity. So your answer will be B. Air resistance cancels the weight of the elephant, so no resultant force acts. Question 48. Which description of the velocity of the moon as it orbits the Earth is correct? Assume the radius of the orbit is constant. Yeah, I've had a bit of an issue with this question because I've just realised the mark scheme is actually wrong on this, so I will go back and possibly adjust a few things, but you'll have to give me a few days for that. The mark scheme, what do they say? I'll just check it now. They're claiming that it's A, the velocity is constant. That's not actually true. Its speed will be constant, but because the moon is always being pulled towards the Earth, its velocity is changing because it's accelerating. It's changing direction. So the answer would actually be C, but I will have to go back and remark those because the mark scheme has clearly got it wrong. Question 49. A gardener pushes their wheelbarrow with a constant force of 6 newtons. If the gardener does 75 joules of work on the wheelbarrow by pushing it, how far does the wheelbarrow travel? So work done, which is energy transferred, can be given by force times the distance moved in the direction of the force. So rearranging this equation, distance is going to be our work done divided by F. The work done is 75, it's all standard units, divided by the force, which was 6, gives us 12.5, so 13 is the closest answer. Your answer will be C. And finally, question 50. Which of the following is a disadvantage of a nuclear energy resource? A, low power output, definitely not. They can very high power output. B, hazardous waste is definitely the problem with them. It's not C, because you can turn a generator on, a nuclear generator, whenever you want, and the technology is actually well understood. It is not something new. Nuclear reactors have been around for 60 years, so we do understand it very well. Okay, that's the end. I will go over the extension question at some other point, but I think that's enough, certainly for this lesson. So you can check your answers and see where you've gone wrong. Thank you very much.